Hi, welcome back to our lecture on a practical guide to quantitative finance interviews. This is our 22nd lecture, and today we are going to talk about Greeks. So basically, all Greeks are just first order or second order partial derivatives of the option price with respect to different underlying factors, which are used to measure the risks as well as potential returns of the financial derivatives. And these are all frequently asked questions during interviews, especially for sell-side quants, because it reflects your intuitive understanding and also your academic understanding of the whole derivative world. And let's first have a review about the Black-Scholes pricing model for options. We call C as what? C is just the Europe call. We just use this European call as a classic example, and it can be written as S multiplied by the ND1 minus K multiplied by a discounted factor multiplied by ND2. And how many random variables are there in total? The first one is S, which is the stock price, right? And we also have K, which is the strike price, but it's a constant, so it's not a random variable. And we also have R, which is the interest rate, could change via time, right? Why we did not consider K is because no matter how time changes, the strike price is still that strike price. And we also have the volatility. Although in Black-Scholes model assumptions, we assume all these two are constant, but in reality, that's not the case, right? And what also do we have? Within tau, we know tau is what? T minus t. This larger t is fixed, but this small t is not, right? It's just time. So it reflects with the time value. So in total, there are 4 variables, okay? And which one is the most important one? Of course, it's the price, right? Price is just the very direct reflection, the most straightforward reflection of the change. It's also the most important thing that you care about. And thus, we have the 5 Greeks. Delta and gamma are all related with S. Delta is just the first order derivative according to S, and gamma is just the second order derivative with respect to the price factor. Okay, and theta is for time, vega is for volatility, and rho is for interest rate. Okay, so we're going to be talking about delta, gamma, theta, and vega in details. But for rho, let's first finish it here. Because in most cases, although interest rate could change, but in most cases, it will only change every 2 or 3 weeks or even months. If, for example, because only the government during their monthly meeting, they are going to give an instruction that there is going to be another 0.25 or 0.5 percentage base point hike, things like that. But the only thing you need to know is that it is positive for call while it is negative for put. Because for interest rate, if the interest rate goes high, basically you get paid more by a call. The cost value is going to increase because you are actually receiving this kind of cash flow if you're buying a call, okay? But if you are buying put, you are buying holding a put, basically it's the same like holding a short position, right? And by holding a short position on any asset, you are basically borrowing money from the bank and you need to pay the interest. Okay, I think that's the most important thing you know. And when the interest rate goes higher and higher, the gap due to the interest rate between the call and the put price is going to be larger. Okay, they are going to diverge. And now let's first talk about delta. So delta, for every derivative, you can actually dissolve this kind of solution by just taking the partial derivative on the original equation, okay? But the delta is just the first order change with respect to the stock price or the asset price. And I'm going to derive this one, for example, but only for delta, because for the others, if you are interested, you can do it by yourself. But I mean, it's complicated and you do not have to do that. No one requires to remember the formula, okay, because it's too complicated. And for Greeks, the most important thing is to remember their market intuitions. So again, for market intuitions, there are two important things that we're going to talk about later. So for each derivative, there are two things. How it changes with respect to, first one is called moneyness, which means if the option is in the money, out of the money, or just at the money. So it is related with K. K is what? K is one of the fixed things that we will not consider, right? And the second thing is time to maturity, which is its relationship with what? Its relationship with larger t, which is another constant that we cannot change. So basically, in the original formula, we have four variables with two constants, and all the Greeks is just trying to talking about to understand how these four variables interact with these two constant. Okay? And they themselves also reflect how those four variables influence the price, influence the price of the option. Okay? So first, let's try to derive this data just for your example. Uh, please notice that to take the partial derivative, we still have the s within this d1 and d2. So actually d1 and d2 are also function of s. So we need to have this dc ds is not going to be just n d1. Okay, it's not just that we kill this s and have n d1. We need to keep these two items still, okay? So it should be, the original equation should be this, which is delta s n d1 minus k e negative rt psi theta s and d2, okay? And actually we know this is going to be d1 n prime d1, which is going to be 1 s sigma multiplied by square root 2 pi tau e negative d1 square divided by 2. Okay? And similarly, we can also find this part is going to be equal to the same parameter, okay? 2 pi tau. And we know the relationship between d1 and d2, right? It's just a d1 minus sigma square root tau square divided by 2. Okay? And combining them together, we can find actually that this part could be canceled out because we are going to have this delta s and d2 is going to be s over k er tau, sorry, and d1. Okay, we are going to have this equation. And because of this one and this one, okay? And combining them together, we can cancel them out and get these two formulas, okay? And now let's go to the next question, which is just we talking about the interaction with moneyness and time to maturity. The question is asked, what is your estimate of the delta of an at-the-money call on a stock without dividend? And what will happen to delta as the at-the-money option approaches the maturity date? Okay, so for the first part, the answer is actually quite easy. It should be 0.5. Why? So if you are in the interview and they're asking you what is delta, do not answer that it's a first order derivative. That's so academic. It makes you like a university student. Of course you are, but a better way to answer is that it's the probability of this option to be in the money, okay? It is the likelihood, probability to be in the money. And of course, when you are at the money, what's the opportunity of being in the money? It's just like a random walk. You are at the initial point 0 and you can go to -1 or +1, each with equal probability of 1/2, okay? So the probability is 0.5. That's the logic behind. And what will happen to delta as the at-the-money option approaches the maturity date? If you don't know or if you forget this kind of picture, of course, I put the picture here so that you can better remember it. But if you do not remember it during the interview because you are too nervous, I think one of the best solution is to think about the extreme case. We think the day at the maturity day. At the maturity day, if it is at the money call, then, and if it exactly at the money, then any price change will suddenly make this as same as the stock, right? If it goes to in the money, or if it becomes out of the money, then this option is going to be valueless, becomes 0, right? Because if it is already at maturity, then it is still out of the money, then you cannot execute it. But if it is in the money, then it will be exactly the same as the underlying asset. So you can see it from the plot. At the very beginning, it is somehow smooth, but the plot is going to be more and more steep, okay? More and more steep, and eventually it is going to be like that, okay? So the delta is going to be what? The delta is going to be changed more, and which gives us the inflection of gamma. Okay, let's first jump over those two questions. Gamma is just the change rate of delta, and the expression is here. So you can see at the money, when time comes to maturity from 3 months to 10 days, it is going to become peak around at the money. Okay, because you can see from delta's plot that it changes most frequently around at the money, and it goes steep to end steep, which means the gamma is going to be higher and higher because it's a change rate of delta. Okay, so now let's go back to the next question. So you just entered a long position for a European call option on this GM stock, which is the General Motor, I assume, and decide to dynamically hedge the position to eliminate the risk from the fluctuation of GM stock price. So how will you hedge the call option? If after your hedge, the price of GM has a sudden increase, how will you balance your hedging options? So that's actually trying to tell you the most classic way of trading options, which is called delta hedge, okay? So basically you can hedge out the influence of stock price, which means no matter the stock is going to increase its value or decrease, no matter it loses 10%, the increase 10%, it's not related to your P&L. You can earn money not from its price, but from something else. That's amazing. That's an amazing concept, okay? Option traders do not like price changes. We can earn money from volatility. We can earn money from gamma. We can earn money from any Greek we want, not just the price. That's the advantage of options that really brings us. And how can we do that? It's actually quite easy. So we already know that delta is going to be this. Sorry. I don't know what's wrong with my pen. Okay, that's cool. Okay, so we already know the delta is just negative r tau and nd1, right? Then we can basically long one asset, long one hand of asset, and then what? And then short 1 over e negative r tau and d1, because this value is usually within 0 to 1. Okay, it's within 0 to 1. So we can show this value of options, right? No matter call or put to make that happen. And it is going to be delta 0. But please remember that the delta hedge only replicates the value and the slope of the option. But you cannot hedge the curvature of the option. If you want to hedge the curvature, you need to hedge gamma as well. But usually when we do the delta hedge, one of the first strategy we can do is gamma scalping. Basically, we want to earn the money from gamma. You know, for gamma, you can see from the pattern, right? We can only infer it if there is a sudden price jump. No matter it is the price jump to high or low, as long as there is a sudden price jump, we can earn some money from gamma, right? Because it's already a signal that it's extremely small. But so basically we can do a delta hedge and we can trying to short the asset while what? While long option, okay? While long a call or a put. And in that case, if there is a sudden price jump, we can earn from gamma. And let's also first talk about theta then. You can see for theta, it's basically the inverse of gamma. So that's what I'm going to tell you now. So theta is the time value, right? And we know time value is decay. And you know, most cases, theta should have opposite sign with gamma. What does this mean? This means that in most cases, you need to sacrifice one for the other. If you want to earn money from sudden price jump, then you must need to long some option. But by long option, no matter call or put, you are losing time value, of course, right? Which means you are losing money from theta. So you can either earn theta or earn gamma. Okay, you can only choose one. 鱼和熊掌不可兼得. But is there any extreme cases? Yes, there is. Like this question said, when will a European option have positive theta? Because if you long a position, it seems to be always negative. But it's already written in this picture. You can see for gamma, it is symmetry, right? This plot is symmetry. But for theta, it is asymmetry. Why is that the case? The case is that for most cases, although the plain call and put, gamma is always positive and theta is almost always negative, but there is case that deep in the money put. Okay, so how is that? If it is direct super in the money, it actually brings the gamma, it actually brings like ND1 prime is almost equal to 0. And N negative D2 will almost around 1. And we know theta, as written here, is noted like this. If we have this case that this is around 0, this is around 0, and this one is around 1. And this is 0, this is 0, this is 1. This could be larger than 0. It actually reflects a hidden thing that we always want more protections. We are loss averse people, right? Which means we are willing to pay more and to protect ourselves. When will we want to buy? Because if you think about it in the first place, when will we want to buy some deep in the money put? It's just a way to protect your long position in that asset. For example, I already buy, let's say, 1 billion on that stock, a long position. But I want to do a hedge that in the case that it suddenly write off, in the case it suddenly become paperless, like New Oriental, Xindongfang back in 2021, just one afternoon, 90% of its stock value just gone because of the regulation change for the China's private education sector, right? So at that time, you can buy some deeply in the money put to help you hedge that. Okay, and you can also buy some deep out of the money put, of course, if you are betting on that. Okay, so we already talked about gamma and theta, but let's go back to delta. We still have one more question. So can you estimate the value of an at-the-money call on a non-dividend paying stock? Assume the interest rate is low and the call has short maturity. So we just need to list out the original formula, okay? So what is our original formula? We have C equal to S N D1 minus K D negative R tau and D2, right? And we already know that as money, so K becomes S. And the thing that we are interested, and we also have this non-dividend paying, and the interest rate is low, then let's assume it's zero. And so this item is gone. So it becomes ND1 minus ND2. And how about this part? For this part, it can be written as D1 to D2, and let's say dx 1 over square root 2 pi e negative 2x squared, right? The density function for the standard normal distribution. So what's the next step? The next step, oh, sorry, it's D1 minus D2. So, okay, D2 should be at the bottom position. It's D1, D2, okay? And when at the money, and for a small r, both D1 and D2 should be close to zero. Why is that the case? Because D2 will become R over sigma minus sigma over 2 multiplied by square root tau. And D1 is just this one plus sigma. So usually it's just R over sigma plus sigma over 2 multiplied by square root tau. Okay, so all of these two is going to close to zero. And if they close to zero, then x is close to zero, right? And when x close to zero, this one is going to be 1. So we can assume this part is 1. So if we assume this is 1, then it just becomes 1 over square root 2 pi d1 minus d2, right? And this is going to be sigma multiplied by tau over square root 2 pi. And this is, it'll be around 0.4 sigma. As tau. Okay? So you get that? I think it's all for the delta part. And in this practice, the approximation is actually used by some volatility traders to estimate the implied volatility of the at-the-money option. Okay, because when we have the price, we can just go all the way back to implied the volatility. Oh, there is no S here, sorry. Oh, no, there is, sorry. 0 because we have the S here. Okay, sigma multiplied by S and multiplied by tau. Cool. So the next one, also about theta. You just enter a long position for a call on GM again and hedge the position by shorting GM shares to make the portfolio delta neutral. So we have the delta hedging. And if there is an immediate increase or sudden decrease in GM's stock price, what will happen to the value of the portfolio? Well, as we mentioned, we have a long position for a call, which means we have what? We have positive gamma. And if there is immediate increase or decrease, then gamma is going to be positive, so we earn some money, right? But is this an arbitrage opportunity? No, it is not an arbitrage opportunity. Why is the case? Because it's not risk-free. We earn gamma by bearing the risk of negative theta. And what in reality is this risk? It means that there is not going to be any sudden immediate increase or decrease. For example, the stock becomes quite flat and there is no jump in the next few months. It's possible, right? And in that case, if you hold the portfolios at that, you actually lose a part of value due to the time, due to theta, and you get nothing from gamma. Okay, so that's one interesting perspective for option trading. And last but not least, Vega. I think Vega is very important. If you ask any traders, and if you go to see the Bloomberg, most of traders do not quote option on their price. They directly quote buy or sell volatility, which means they buy or sell according to Vega, right? So for volatility, of course, at the money options, you already see the delta and the gamma plot. They are most sensitive to volatility changes. So of course, they have higher vigor than either in the money or out of the money options. But the vigors of all options decrease as time to expiration because when the term goes longer, you actually have higher volatility. That's also the reason why the US 10-year Treasury bond will always have higher, in most of the cases, okay, not always, because currently we're actually having a higher interest rate for its 1 year or 2 year short-term bond Treasury. But the most important thing is the implied volatility and smart curve. So it's not about Vega, okay? Please be clear about Vega and volatility itself. Vega is the change rate of volatility. But for implied volatility, it also have this classic smart curve. It means that when we are at the money, the volatility is at its lowest level, but it changes the fastest. Okay, it's itself is at the lowest level, the minimum, but it changes the fast. Okay, but it is trying to describe the relationship between the strike price and volatility. Okay, and if you also the money, then well, the volatility actually goes higher and higher. So, but in the first place, what is implied volatility? We know that the in Black-Scholes models, we assume this is going to be constant. But in reality, it's not, right? So in reality, we have the price. So we put back in the Black-Scholes model to have the implied one. And we call it implied volatility. And you can see on the right-hand side, there is also a thing called a smart curve. So what is a smart curve? A smart curve is that for stocks, especially for stocks, actually the curve usually looks in this way, okay? It is not going to be small on both hands. Why it is the case? Because lots of people, as I just mentioned, they buy protective position. So which means people are much more willing to pay for the downside risk than do long speculation, okay? Downside protection was more valuable than upside speculation. And thus the volatility is higher because only if there are people trading it, the volatility could be high, right? So let's see two questions. The first one is that you have to price a European call option either with constant volatility 30% or by drawing volatility from a random distribution with a mean of 30%. Which option would be more expensive? So the first one is to have a constant volatility, which is just the expectation of volatility multiplied by this call. And we know that for a call option, it is a concave function. It is a what it is it concave or it is convex? It is convex, right? So we remember we still have this inequality. And basically this is just the volatility from a random distribution. This is a constant distribution, right? So in most cases, this one should be more expensive. But it could also be possible that this core is concave. How could that be? It could be that for cases where we have D1 larger than 0 and D2 smaller than 0. And in that case, it's possible for the value of the core to be, it's possible for it to be concave. You just need to take the second order according to the volatility sigma. And actually it is this one. Is volatility multiplied by sigma D1, D2. Okay, this is called Volga. This is called Volga. This is just Vega. Okay, this is Vega. So we know Vega is positive, right? For all options, of course, it is positive. And we have this constant item. We have the sigma here, which is also positive. So basically, the sign of this thing is determined by dy and d2. Since it determines the convexity, this is going to determine the curvature. Okay, this is going to determine the curvature. So if it is possible that D1 larger than 0 and D2 smaller than 0, then it could be looked in this way, right? Because this was smaller than 0. Okay, so last question, the risk neutral measurement. The Black-Schoen formula for non-dividend paying stocks assumes that the stock follows a geometric Brownian motion. Now assume you don't know the stochastic process followed by the stock price, but you have the European core prices for all strike price K. Basically, it's in the real market, you have all the price, right? You have the K. Can you determine the risk neutral probability density function of the stock price at time T? Well, that's actually a simple one. So what you need to do is just to match each other, okay? Let's go back to the first place. The core option is just E negative R tau and take the integration from K to infinity. Do you still remember that? S minus K, right? Multiplied by the density function of ST as dST, which is the density function of the stock price, okay? And taking the first and the second derivative of C according to K, you are going to have this thing. E negative R tau K to infinity And this is just a negative k, so it is just a negative f s t s ds. Okay, and how about the second derivative? The second derivative is just e negative r tau f s t. It is going to become, and so we only have one here, so it will become k. Right? So what can you find? We can find that f s t k. Okay, so we can have the function of that. So this is the risk neutral probability density function of the stock price at time t, right? Because we have average strike price k, then basically if we have average strike price, then we can have also for every price, right? Because it's just a map. And we know it is just E R tau and the second derivatives of this call option according to k. Okay, so you are just trying to change this one to k by taking derivatives. It's actually a good mathematical way to solve certain problems. That's all for Greeks, and I hope you enjoy it. See you next time. Next time, we are going to talk about some option portfolios and exotic options. Okay, see you.